Hello. This is lecture 14A for Calculus 1. My name is Scott Grizzard from the University of South Florida. So last time we focused on the Riemann integral and we defined the Riemann integral. And then we did the notation for the integral. Today what we're going to do is we're going to do notations for antiderivatives, the indefinite integral. We're going to talk about that briefly. We're going to do bar notation, so just a little bit of cleanup. And then we're going to talk about the consequences of the integral being area. Remember, this is the area under the curve, and the emphasis is on area. Signed area, yes, right? You can have negative area. But the point is, because it's area, it's going to mean that there are a whole bunch of properties of the integral that we can talk about, which come from the fact that it's area. Let me just say what's left here because we're nearing the end of the course. So we're going to be talking about area properties of the integral. That's today. Next time, we're going to prove the fundamental theorem of calculus. And that is a very cool lecture. You're not going to want to miss that. Then what we're going to do in 15A is we're going to talk about undoing the chain rule, use substitution. And then for 15B, we're going to talk about initial value conditions and another way to solve initial value problems. So we talked about taking the antiderivative and then solving for the constant. We're actually going to look at another way to look at those. And I alluded to it when I did the course, but there's an interesting other way of thinking about that using the fundamental theorem of calculus. That's actually much more useful. It's less useful on tests, but it's good, but it's very, very useful in real life. Okay. So what we're going to talk about today, again, we're going to talk about some notation. We're going to talk about the consequences, and then we're going to show some of these properties also hold from indefinite integrals for antiderivatives. And then we're going to do a little bit of cleanup too. There are a bunch of little topics in here. Okay, so just to remind you that I had this idea of the Riemann, the integral. And I had a definition for it. And I said if f was continuous, then we'll define the area under the curve, fa of x is equal to the integral from a to x of f of t dt. And because of this, we're actually going to define, remember I have the fundamental theorem of calculus part 2, which says that if g is some antiderivative, well, then I might as well just use this notation. So instead of saying f negative 1 of x, we have this kind of s piece of f of x dx with no endpoints. That's the indefinite integral. So that's just another notation for the antiderivative. Okay. The indefinite integral, the antiderivative, two words for the same thing. And two notations for the exact same thing. Okay. So we can rewrite the fundamental theorem of calculus to say if f is continuous on D and g is some antiderivative, then we can change this instead of AUC FA of x, instead of the derivative of that being f of x, we'll say that the derivative with respect to x of a to x. And notice that this x and this x, the action actually happens. The thing that's moving is this top point. That's the thing that's moving. That's where the action is. And then we have this other notation, which is bar notation, which you've seen on WebAssign, which is to say the g of t evaluated from x to a. So g of t, a to x equals g of x. It's just another way of writing that particular notation. You can see I did this here. So I had g of x where x equals 3 is this. G of x from 3 to 4 is g of 4 minus g of 3. And this notation just is because of the fundamental theorem of calculus. That's why the notation exists. Okay, so here's an example. If I'm going from 2 to 4, x squared dx, what I'm going to do is I'm going to take the antiderivative with the constant being 0. I'm going to up the exponent by 1 and then multiply by the reciprocal of the new exponent. So I get x cubed times 1 over 3 evaluated from 2 to 4. So it's the fundamental theorem of calculus says I take the base point, I take the x, the top value, and I subtract it by the value at the exponent at the base point. So I get 4 cubed over 3. That's this evaluated at 4 minus this evaluated at 2, 2 cubed over 3. And I wind up with the number 56 over 3. Okay. So again, what I want to focus on are the consequences of the fact that this is area. So one of those things is that sometimes I don't need to do fundamental theorem of calculus. I don't even need to do that. What I can do is I could just think of, okay, 1 minus x squared, that's a circle, right? That's half a circle. So what I'm going to do is just say, okay, well, that's the upper half circle, and I'm going from 0 to 1, right? So recall that. So that's a circle with radius r. So that's the same thing right there as a circle with radius r. Okay. And then so y equals square root of r squared minus x is the top half. And y equals the negative square root of r squared minus x squared is the bottom half. So here I've got the half of a circle of radius 1, or square root of 1, which is just 1. And what I want is the area from 0 to 1. So the key, if you're going to use this bit, draw it out. So if you get a problem, you're not quite sure how to evaluate the integral, graph it if you can. And if you have something like this, that's a circle. And just remember that's a circle. So the key to this bit is to draw it out. Here, this area right here is going to be the quarter of the circle. So I'm going to have 1 quarter pi r squared, which is going to give me pi over 4. And there's the diagram for it. So go ahead and hit pause and compute the integrals from negative 2 to 2 of 4 minus x squared and negative 3 to 0 of negative square root of 9 minus t squared. These are both circles. This is going to be a quarter circle, and figure out which half. And this is going to be the whole half circle. Figure out which half. Okay, well, because this is area, okay, I can add horizontally. In other words, let's say I can take this piece here and I can add that piece there. So this right here is f of x equals the absolute value of x. And what I have is 2 triangles, and I can add those. Okay? But this has a very technical meaning. It means that the integral from a to c of f of t dt equals the integral of a to b of f of t dt plus b to c f of t dt. And just as a note, we're going to use this little fact, the fact that I'm dealing with area, this kind of obvious idea that I could take this piece and add to this piece, right? So the integral from negative 1 to 2 is the integral from negative 1 to 0 plus the integral from 0 to 2. And we're actually going to use this very kind of elementary fact to help prove FTC, the fundamental theorem of calculus next time. So here was my example. I go from negative 1 to 2 of the absolute value of x dx. Well, that's the same thing as negative 1 to 0 of the absolute value of x. And that's plus 0 to 2 absolute value of x. Now, from negative 1 to 0, this right here is negative x. From 0 to 2, this right here is positive x. So I apply a little fundamental theorem of calculus, and I wind up with these calculations. And you could just remember it's this triangle plus that triangle. But I actually worked it out. It didn't have to be 2 triangles, right? Because I could have had it be something like the absolute value of x cubed, which would have given me something that looks almost like a parabola, but isn't quite. But you have to split it up into its 2 pieces. So as I say, here's the absolute value of x cubed. Now, if I wanted to do this, what I would do is I'd split it up into this integral here, which is the absolute value, which is, right? So this bit here, if x is less than 0, right? If x is less than 0, I'm going to want y equals x is negative x cubed. So I want this piece here. And if x was greater than 0, I want that piece there. So that's how you would evaluate the integral from whatever you had. If you had the absolute value of x cubed, you'd split it into this piece, and then evaluate the integral. Okay. Again, here's another piecewise function. I've got f of x equals the square root of 1 minus x squared if x is between -1 and 1, and x minus 1 if x is greater than 1. So this piece right here is a quarter circle. This piece right here is a triangle. And what I'm going to do is I'm going to split this up into its component pieces. So if I want to evaluate the integral from 0 to 2, I'm going to take the integral from 0 to 1 of this piece, plus the integral from 1 to 2 of that piece. So as I said, I can add horizontally. I can, if I've got an intermediate point, I can just, go from A to B and then go from B to C and add the areas together. I can also add vertically, which means that the integral from A to B of f of t plus g of t dt is the same thing as from A to B of f of t dt plus a to b g of t dt. So in other words, if I've got this function right here from -1 to 1 of the square root of 1 minus x squared plus 1, what I really have is half a circle plus a rectangle. And I could break it up as half a circle plus a rectangle. It's area. The next thing, if I have no width, I have no area. Believe it or not, this we're going to use. That's actually, an important bit for the proof of FTC, believe it or not. It's one of the little pieces. So if I go back here, right, here's my, we saw this before, my area under the curve. Right, so here this base point here is 0. If I run this back to 0, I have no width. Here, let's do this again. Here I actually have height, right? F of 0 equals 2. My value is there. So if I was splitting this up into rectangles using this left endpoint, I'd have a rectangle right there. But if my width is 0, right? If I go all the way back, if AUC F0 of 0.3, that's something here. But if I go AUC F0 of 0, I'm going to get 0 because I have no width. Likewise, here, my base point was 1 again. And if I back this up all the way to 1, if I back x back up to 1, I'm going from 1 to 1, I've got no width. Here, I started here, I hit play, but so I've got negative area, but I'm heading toward 2, which is my base point. Once I reach 2, my area under the curve is 0 because I have no width. Okay? That's actually a big thing. If I have no width, I have no area. From A to A, f of t dt. Something that's obvious, but it's one of those things you can forget. Now, the next thing is that if I switch the endpoints, I negate it, right? Because remember that what's going to happen here is that area that's left of the base point suddenly becomes area that's right of the base point, and vice versa. So the signs flip. Remember, when I go left of the base point, I flip the sign. Okay? So that means that if I start here from 0 to 4.5, if instead my base point is 4.5 and I'm coming from 0, I'm going to have negative area wherever there was positive area and positive area wherever there was negative area. Okay? So if I flip my endpoints, if I flip my base point and my upper point, or my upper point because it appears upper there, not because it's right of the base point. It could be left of the base point, but the point is it's the moving point, right? So if I go from A to B and I flip it from B to A, negative area will become positive area and positive area will become negative area. So I just negate the whole thing. All right, the constant multiple rule. Okay, this is one that we're actually just going to take from antiderivatives, right? If I have the constant here of f of x dx, if I have c times f of x dx, remember that if I have a derivative, I just move the constant across. Well, the same thing happens for antiderivatives. Well, because it happens for antiderivatives, it's going to work for area under the curve. Because remember, the area under the curve is just the antiderivative. We have to pick the constant. It's a specific antiderivative. Okay, the book presents this a little bit differently, but it's called the limit property. It's how you deal with jump discontinuities. And again, this is going to be more of a Calc 2 thing, but I'm going to talk about it right now. Let f be defined and continuous on a, comma, b. Then the limit as x goes to b of a to x f of t dt equals the integral from a to b f of t dt, even though it may be infinite. Okay? In other words, I can just take it to the limit. Okay, so here's an example of a finite. I have a jump discontinuity here, and this rule says that 0 to 3 f of t dt equals the limit. Remember, I'm going to split this up. I'm going to take the limit as x goes to 1 of 0 to x f of t dt, that's there to there, plus 1 to 3 of f of t dt. Well, what I'm saying is that I can just take the limit. I'm going to get 0 of 1 of 1 dt. And the important thing is here, 1, this piece actually is continuous if I included the endpoint. Okay? So I split this into the two pieces, and then I take the endpoint. And here I've got 1 to 3 of 2 dt. That's the function 2. So in other words, I can just fill in the point in one sense. Now here's an example of an infinite one. Let's go -1 to 0 of 0 left of 1 over x dx. Well, this is going to be the limit as x goes to 0 of -1 to x of 1 over t dt. Okay, so I'm taking the limit. Well, by FTC2, I'm going to get the limit as x goes. I'm just going to deal with this piece here. I'm going to get the log of 1 times the absolute value of t evaluated from x to -1, or -1 to x. So now I take this limit here, and I'm going to wind up with negative infinity minus 0, which is just negative infinity. And this is actually very useful in Calc 2. You can use this. So you can use this to show that that this particular series diverges, which is one of those like cool things in Calc 2. So it's going to you can show it very quickly by using this little trick with the integral. Okay, so those are sort of the properties. And remember that properties 1 through, don't get distracted by property 7. 1 through 6 are the really important ones. All right, well, because I have these definite integral properties, I also get a bunch of indefinite integral properties. Oops, wrong one. So, this constant multiple rule one I've already mentioned, but this one right here, this rule right here also applies to antiderivatives. So I have a sum rule for antiderivatives. If I have the antiderivative of f of x plus g of x dx, I can split that up there. Okay. The other one that really applies here is the constant multiple rule. And that works for antiderivatives. So I've got two of these work very well for antiderivatives. Okay. So let's now flip our things and do a couple more examples with the FTC using this new notation. So if I want to do the integral from 0 to pi of sine of t dt, what I'm going to get is negative cosine of t by FTC2, right? The antiderivative of sine is negative cosine, and you should make a chart like this on the exam so that you can help yourself quickly. And that's going to equal cosine of t from 0 to pi. So I've got negative cosine of t. So I've got negative cosine of pi minus cosine of 0. I wind up with 2. Here's the same thing. I apply FTC2 to this one and work this out on your own, but I split it up and then I apply FTC2 to the parts. Now here's some examples of using the fundamental theorem of calculus part 1. Here I've got the derivative with respect to x of 0 to x of sine of t dt. Well, f here, remember the notation change. This is the area under the curve, under the sine curve from 0 to x. So the derivative of this by FTC1 is simply sine of x. Now here I'm going to throw a curveball. Again, I mentioned that this is where the action is, right? If you look at it this, from 0 to x squared sine of t dt, remember that this is where the action is. So I'm going to rewrite this as AUC f0 of x squared. Now you can see the chain going on. So I apply my chain rule, and I'm going to have the f of u times the derivative with respect to x of x squared. That's going to be sine of u times 2x, which is sine of x squared times 2x. This one, on the other hand, has no chain because the t squared is the thing getting changed. So the derivative with respect to x of 0 to x of sine of t squared dt is simply sine of x squared. There's no chain. I just take the x and I plug it into the function. This is where the action is, that upper point, which was part of the point of doing the AUC notation. Okay, this is where the x is. That's where the action is, right there and right there when you're using FTC1. Okay. I can also use the rules that I just had, and these are the tricky ones, to multiply, to alter the integral. So let's say I want to do the derivative with respect to x. Now notice here the base point is the thing moving. That's weird for this thing, right? And FTC1 cannot be applied to this. But if I flip the base point and the upper point, I actually get d over dx of negative 0 to x sine of t dt. And that I could take the derivative of using FTC1, and I wind up with negative sine of x. Okay, so that's what I have for you today. We talked about the area properties. We talked about some new notation. We talked about these area properties, and I mentioned that a few of these are going to be very important next time. So I mentioned this idea of adding horizontally is going to be important for us next time. And then this very simple idea that if I have no width, I have no area. And we're going to use that next time when we do the proof of the fundamental theorem of calculus. Okay, next time what we're going to do is the fundamental theorem of calculus. We're going to prove it. You want to see that because that's just cool. We're going to use a bunch of stuff that we haven't seen, like something from the beginning of the class we're going to now use, along with a bunch of other stuff that we've talked about, like the fact that antiderivatives are vertical shifts of each other and those sorts of things. And we're actually going to prove the fundamental theorem of calculus. It's kind of the big end all of the course. So I will see you next time for that. I'll have notes for you for that next one too. All right, see you next time. Bye.